Hey, welcome to AP Physics 1 screencast for springs. I don't have a Bozeman video for you guys to watch, so let's just get right into the video, into the slides here. So springs, a lot of this is going to come back from simple harmonic motion, which was the first screencast I gave you guys. So I'll kind of go quickly through that part of this. So we already talked about Hooke's law. Force is equal to negative kx. Remember, the negative just denotes that the displacement is in the opposite direction of the force acting. And work energy in springs. This is also a little bit of a review here. As you're stretching out that spring, the force is going to increase. Like I said before, think of a slinky that you're stretching out. The farther you stretch it, the more it's going to resist that. So the more the displacement, the more the force is required, and that's baked into Hooke's law there. Work must be done on the string to stretch it because you are applying a force over a distance, and therefore that is work. And also, the stretched spring can do work on an object as it returns to equilibrium. And I'm going to give you a kind of a diagram of that here in a little bit. What this is going to end up giving us is this new term we have: elastic potential energy. So you think if you have a coil and you compress it, compress it inward, that once you release that thing, it has the potential to shoot something out. Think of a toy gun, which is the classwork problem we're going to look at. That is elastic potential energy that you are storing in that spring until you release it. Something like this. So if you have a coil and you push it against the wall, as you're pushing that, you're doing work on that coil and on that spring. And the farther you push that in, that's an increasing applied force. To get that increased displacement, you have to increase your force applied. So it's not just a constant force here. And so I push this ball in front of it. And I have potential energy inside that coil. Well, once I release that, it's going to shoot that ball off, much like that. And so as it shoots that ball off, something that's a little bit different is the work is being done by a decreasing spring force, because as that spring starts to return to its equilibrium, there's going to be less and less force on that. So the maximum force you're going to have is right at that release point, and then it's going to decrease from there on out. So how much work is being done on or by the spring? Well, normally we say, okay, work is force times displacement, or Ft cosine theta. It's a little bit different here because, as we mentioned, the more displacement we have, look what happens. We have more force. So it's not a constant force. So we can't use force times displacement in this case. We have to have another formula. And that's where we're going next. We can actually do this mathematically fairly straightforward. So if we say that the force that's happening is anywhere from 0, which is the very start, to F, which is my maximum force. Well, let's just average that out and say it's 1/2 F, or F divided by 2. So going with the original work equals FD, I can substitute that in F over 2 times X. So I end up with 1/2 Fx. Well, we also learned earlier that F force is equal to K times X when we're looking at a spring, Hooke's law. So let's kind of put that into here. So 1/2 times Kx times X. Well, we just finish up the algebra and we have a new formula. Work is equal to 1/2 Kx squared, and that is also equal to the elastic potential energy. How does that work? Well, think back to the work energy theorem. Work energy theorem was work is equal to the change in kinetic energy. Well, my change in kinetic energy in this case is going to also be equal to my elastic potential energy, because what happens is, if you imagine that spring releasing and shooting off that ball, well, that change in kinetic energy is equal to the elastic potential energy that I put into that spring. So we can equate these two things. And then also, just for reference, we can also use the area under the curve to find that. And we can also show that mathematically. Well, in this case, we have a triangle, so 1/2 base times height. Well, my base times height, my base is X, and my height is F. So I can put that into there, X times F, and then do the same thing I did in the previous slide. F is equal to Kx 1 half kx squared. So that's a really handy tool that you can use for that as well. Um, yeah, pretty short. Let me show you, this is the Hooke's Law PHET I use for SHM. This is under energy this time. So this is really cool. You have kind of this curve of the energy. Let me show you how that's working. So as I'm pushing in, I have an increasing force, and the more I push this in, notice the more that force is increasing. So I have an exponential increase there. And then as I increase the spring constant, think about what do you think is going to happen? Where's that line going to go? It's going to go up because I have to increase the force. If I have an increased spring constant, I have to have more force to get the same displacement. And in this case, that's also going to increase the energy because because of the formula we had there. All right, and also, I was going to show you this as well. We can look at this on a force plot as well. So it's really cool. You can see the slope there. Remember the slope, what is the slope? It is K. Don't forget that. On a force versus displacement graph, your slope is going to be your spring constant. And we can even show, hey, there's the energy by finding the area under the curve. Really cool. All right, let's take a look at your classwork problem here. A toy dart gun has a spring with a constant of 50 newtons per meter. When loading a dart, the spring is compressed 3 centimeters. Each dart has a mass of 10 grams. So we want to know the work required to load the dart, the maximum acceleration, and the muzzle speed. Muzzle speed, if you're not familiar with guns, is just basically what is the speed of this projectile as it leaves the barrel. Because after that, it's just going to slow down. Remember projectile motion. So it's kind of the maximum speed we're looking at there. So we need to list our variables here. 50 newtons per meter is my spring constant. Displacement is 3 centimeters, but I need to convert that to meters, so 0.03. Mass is 10 grams, which is 0.01 kilograms. And that's a diagram what we're looking at. If you can imagine with a spring gun there, that's compressed like that. So 3 centimeters is my compression. And once I click the trigger, that's going to shoot out like that. So for part A of that, I am finding the work required. Well, the work is just straightforward. 1 half kx squared. 50 is k. My x is my displacement there, 0.03. So that gives me 0.023 joules. And remember, that is also the elastic potential energy that I put into that spring that's going to cause the change in motion of the ball. Part B of this, what's the maximum acceleration rate? Okay, remember the maximum acceleration rate is when you're going to have the maximum force. So where do you have the maximum force? It's right after that spring releases because it's going to decrease as it gets closer to its equilibrium point again. So we take we want to find the force at that point. So 50 times 0.03, force equals kx. That means I have a maximum force of 1.5 newtons. And then I can just go straight to F equals ma. That force is acting on a 0.01 kilogram projectile. So my acceleration is 150 meters per second squared. Sounds pretty fast, but remember, you got a small thing going very fast, so that shouldn't be too outlandish there. Last part here, the muzzle speed. So whenever we're talking about speed, what type of energy are we going to want there? Well, we want kinetic energy because kinetic energy, 1 half mv squared. So remember that the elastic potential energy we found in part A, and when I release that trigger, that elastic potential energy converts to kinetic energy. So EPE1 equals KE2. And then once I know that, it's really simple. I just plug that value in, 0.023 equals 1 half mv squared, solve for v, and I get 2.14 meters per second. All right, guys, so just let me know if you have any questions, feedback, or whatever. I'm here for you. See you later.